Hello guys, welcome to my channel Learning with Saritha. It's my pleasure in presenting a video on the topic Gauss law. Gauss law is applicable only to the enclosed charges. That is, the electric charges must be inside a closed surface. And the closed surface can be of a perfectly shaped closed surface or arbitrary shaped closed surface. Here are some perfectly shaped closed surfaces. For perfectly shaped closed surfaces, we can say a sphere. Sphere is perfectly shaped, isn't it? It's perfectly shaped closed surface. And for other perfectly shaped closed surface, we can say a closed cylinder. See, the cylinder is a perfectly shaped, but it should be closed on both the sides. And a cone is also a perfectly shaped closed surface. The top of the cone must be closed. Okay. And a cube is also a closed surface, and see here it's closed in all the sides. For arbitrary shaped closed surface, we can choose any random shape. Even a sphere, if it is pressed on its sides, we can say it is a random shaped closed surface. See here, I have pressed a sphere on its sides and we can say this is a randomly shaped closed surface, isn't it? All the sides are closed but not perfectly shaped, that's all. And in this topic, we are going to learn how far this Gauss law is applicable to perfectly shaped closed surfaces and to arbitrary shaped closed surface. First, we will learn the Gauss law for perfectly shaped closed surfaces. For this, we consider a positive charge. That is, the positive point charge is a strong source charge. The electric field lines from this point charge will be pointing outwards radially in all directions. Now, for a particular radius r, what will be the surface formed? For the radius to be equal on all the sides, we get a sphere, and the sphere is closed spherical surface. And this imaginary closed spherical surface for a particular radius r for a point charge is called a Gaussian surface. That is, we get the imaginary closed spherical surface called Gaussian surface. The electric field lines which are radially outwards come out of this Gaussian surface, isn't it? Now, we are going to find the number of electric field lines which are coming out of this Gaussian surface. That is, we are going to find the electric flux. To find the electric flux, we have to split the surface into smaller area elements. Here, the area element dA, infinitesimally small area element. The area element and the electric field are perpendicular to each other. We know the nature of the electric field. It has both magnitude and direction. The direction of the electric field will be perpendicular to the surface, and to the value, that is the magnitude of the field, will be constant on the surface, will be equal on the surface. And so the electric field E and the area element are said to be perpendicular or normal to each other. Here we have just said about the area element, not the direction of the area element. But to find the electric flux, we need the direction of the area element. So, the direction of the area element will be at an angle of 90 degree from the surface of the area element. Now, what will be the direction of the area element and the electric field? They both will be pointing in the same direction, and there is no angle between the direction of the area element and the electric field. That is, theta will be 0 when the direction of area element and the electric field are parallel to each other. Now, the electric flux through a closed surface of the sphere phi e is given by the expression closed integral E vector dot dA vector, because we are choosing all the area elements of the whole sphere. Okay, that's what we have written, closed integral. And what about the dot product of these two vectors, E vector and dA vector? We can write it in the form of a scalar E dA cos theta, but theta representing the angle between electric field and the direction of the area element. Since they both are parallel, the theta value is 0. Now what will be the flux? Phi E is equal to closed integral E dA. And we know that the field is uniform on the surface. So it can be taken out of this integral. So phi E is equal to E dA. E closed integral dA. Now what we have to do is we have to find expressions for this electric field E and closed integral dA. This electric field E is nothing but the electric field at a point due to charge Q. We have learned earlier. You see, you consider a charge. This is a point charge, strong source charge. It will be radiating electric field lines outwards. When we place a test charge, I represent by small q at a point P. Now, there will be a Coulomb force of attraction or repulsion between these two charges. Here, since my source charge is positive, there will be a repulsive Coulomb force between these two charges. What is the Coulomb force between capital Q and small q? That is between the point charge and the unit charge. Okay, now F vector is equal to K Q by R square R unit. Now what is the field at this point? The field is the force experienced by the test charge at this point. So E vector is equal to F vector by Q. And the expression becomes K Q by R square into Q. R unit representing the direction. And E vector is equal to 1 by 4 pi epsilon naught Q by R square R unit. And this expression for electric field gives both magnitude and direction of the field. Now for finding the electric flux phi E, we need the magnitude of the electric field alone, isn't it? Here there is no vector notation. We have changed the dot product of two vector into a scalar. So we need only the magnitude. So I take the magnitude value alone. That is, I remove the vector notation and the R unit notation. So E is equal to 1 by 4 pi epsilon naught Q by R square. Now I got the value expression for E. Now what will be the expression for closed integral dA? This dA is representing a sphere, isn't it? Here we enclosed a charge, point charge, and it formed a spherical surface. Now what is the area of the sphere? The surface area of the sphere is equal to 4 pi R square. Okay. So we are going to substitute the expressions for E and closed integral dA in the electric flux expression. What we get? Phi E is equal to 1 by 4 pi epsilon naught Q by R square into 4 pi R square. Here 4 pi and 4 pi gets cancelled and R square gets cancelled, and flux phi E becomes Q by epsilon naught. Okay. Here the Q is nothing but the enclosed charge and epsilon naught is the permittivity of the free space. Now the expression for electric flux by Gauss law is given by 1 by epsilon naught times the charge enclosed within the closed surface. That is, the Gauss law is giving the relationship between the total flux passing through the closed surface. That is the number of electric field lines passing through the closed surface and the net charge enclosed within the surface. Next we are going to see how far the Gauss law is applicable to the arbitrarily shaped closed surfaces. Consider a charge Q enclosed in an arbitrary closed surface. Here you see the shapes are not perfectly shaped and the charge is enclosed within it. First we imagine a perfectly shaped sphere. of radius r, and it possesses an area A1. Some electric field lines are coming out of this area. Okay, next we are increasing the radius, and the shape is also arbitrary, and it possesses an area A2. And next, for further increase of radius, the area element A3, the area A3 is formed, which is also arbitrary. Now our question is the electric flux, that is the electric field lines coming out of this A1, A2, A3 are same or not? According to Gauss law, as the radius is going on increasing, we can write R as NR, that is N times R is increased. And on finding the area for that radius term, we have to use NR instead of R. Okay. Here what is the value of R? That same value must be given on calculating the area. And we know that for electric flux calculation, the radius terms gets cancelled. So again, what will be the electric flux? It will be Q enclosed by epsilon naught. So for an arbitrary shaped closed surface, the net electric flux is same for all the surfaces. Important inferences of Gauss law. First, electric flux is independent of the charges present outside the closed surface. So far we learned that the charge is enclosed in the closed surface, isn't it? Now I have placed the charge outside the closed surface. The charge will be radiating electric field lines, and I place a closed surface here. The electric field line will tend to penetrate into the closed surface on one side of the surface, and it will penetrate out of the closed surface through the other side of the closed surface. Okay, now what will be the angle on the penetrating inside? You see, the electric field line E vector is pointing in this direction, and the direction of the area element is pointing in the outward direction of the closed surface. That is, it's exactly opposite to the direction of the electric field. So the angle between E vector and dA vector will be 180 degree. The electric flux phi E will be negative of EA. Okay. Now what happens on the penetrating outside? Here the direction of the area element and the E vector are both in the same direction, and so there is no angle between dA vector and E vector. They both are parallel, and so theta is equal to 0. So the electric flux phi E will be positive of EA. So the net flux will be 0. So what we learned from here, the electric flux is independent of the charges that are present outside the closed surface, and Gauss law says only about the charges that are present inside and not on the outside. So according to Gauss law, the electric flux is independent of the charges present outside the closed surface. Second, electric flux is independent of shape and size of the closed surface. Here you see, here is an imaginary perfectly shaped closed surface. Here I have an arbitrary shaped closed surface. Here a closed cylinder, a closed cone, and a closed cube. If a charge is enclosed within here, what will be the electric flux? Electric flux phi E will be 1 by epsilon naught times the charge enclosed. Whatever be the shape and whatever be the size, the electric flux is independent of it. Okay, and according to Gauss law, the electric flux phi E will be 1 by epsilon naught times the charge enclosed within the closed surfaces. Third one, electric flux is independent of the location of the enclosed charges. Here you see I have placed the charge at the center. In this case, the flux phi E is Q enclosed by epsilon naught, And 2, if the charge is placed somewhere else other than the center, here also the flux phi E will be 1 by epsilon naught times Q enclosed. Okay, and the next point is the Gaussian surface is dependent on symmetric charge configuration. That is, it takes a symmetric shape. It is a must in the case of a Gaussian surface. If the charge is a point charge, the symmetry formed is spherical symmetry. And if the charge is of linear charge, the symmetry formed is a cylindrical symmetry. And if the charges are distributed on a plane, the symmetry formed is a planar symmetry. Okay, that is, Gaussian surface is dependent on symmetric charge configuration. Next one, electric field is due to all the charges present inside and outside the Gaussian surface. In this point, we are going to talk about the electric field. Okay, what about the electric field? Now, we consider charges Q1, Q2, Q3, Q4 and Q5 inside a closed surface. And there are also some charges outside the closed surface. Now, the doubt arises is the electric field E vector, which we use for calculating the electric flux. The electric field E vector is formed by the charges inside the closed surface or the charges outside the closed surface. This is what the doubt we have. Here you see the total electric field of all the charges both inside and outside the surface or giving the resultant electric field. That is, the resultant electric field is the E vector which we use in the expression for finding the electric flux phi E. Okay, the electric field is due to all the charges present inside and outside the Gaussian surface. But when calculating the electric flux, the charges which are present outside will not contribute any flux. Only the charges present inside will contribute. So, according to Gauss law, the charges enclosed must be considered for finding the electric flux. Okay, that is, by Gauss law, flux phi E is equal to 1 by epsilon naught times Q enclosed, and for all the charges enclosed must be taken as a total and divided by epsilon naught. That is, electric flux phi E is for all the enclosed charges and the electric field E is due to all the charges present inside and outside the closed surface. Okay guys, I finish up here. I hope you all understood all the concepts of Gauss law easily. After watching my video, just click the like button, share my video and subscribe to my channel and travel with me to get full mark easily. Thank you.